Mechanics of solids, section 3, mechanical properties of materials. We discussed about two chapters or sections. The first one was stress, defining the concept of a stress. We said it's a type of internal pressure at any imaginary section of an object, and we categorize them into normal stress and shear stress. Then we talked about strain, that is a concept of deformation caused from a stress at any object, and the normal stress, we defined it would be the deformational ratio of the of an object from a normal stress application, and the shear strain was the deformational ratio in the content of distortion from the shear strain. So, well, and then we mentioned that the first three chapters are our fundamentals. So in our fundamentals, we learned about stress and also the strain. And now in chapter 3, we want to get more knowledge about the property and the strength of materials, right? So in chapter 1, we mentioned that, okay, so a system or an object is under a stress. In chapter 2, we mentioned that this object will get deformation in the um, um, with the concept of a strain. And in chapter 3, we'll talk, okay, how strong is this object in order to tolerate this stress. If the object is stronger, the epsilon or strain is lower. If the object is weaker, your strain is higher. So there is a correlation between the strength of the material and the amount of that material experiences the deformation once you apply a stress on that. So the property of the strength, in engineering, we always want to quantify characteristics, right? We want to have measurements. We want to have values, put values. I'm talking this object number 1 is stronger than number 2. How much? What's the value of that strength? Well, how we characterize that strength? That's the ultimate goal of an engineer. Characterization of the real world. However, if we don't do that, we already know, okay, so object 1 is stronger than 2. It's just a qualification of that. But in the modern science, in modern engineering, we want to characterize that. So in order for characterization, we see that actually there is a correlation between stress and a strain. And with that correlation, we can actually characterize the strength of materials, right? So that being said, stress, strain. If material object 1 is stronger with the same amount of stress, you have lower strain. If it's weaker with the same amount of stress, you have higher strain. So there is a correlation. You can apply or develop a correlation between a stress and a strain to characterize the strength of your materials. So that's what we are going to discuss here in chapter 3. This is an outline for this chapter. So the first outline we'll talk about, the first topic we'll talk will be material characteristics, or how we are actually characterizing different materials. We'll start with steel, as it's a little bit more straightforward, and we develop our foundation of how we calculate and measure the material characteristics for steel, and then we're gonna expand it to other materials. In this section, I will talk about, let's say, aluminum or concrete or wood or different types of materials. That's gonna be same procedure, but obviously these are different materials, and therefore their mechanics and their strength will be different. But we'll start with the steel, as it's more like just more general and we better example to start with. And then we'll talk about a stress strain diagram. So we said actually, I mentioned that the strength we can develop the strength of the material by developing a correlation between a stress and a strain. So that's actually what it is called as stress strain diagram. And from a stress strain diagram, we can learn a lot about the properties of material as we are going to discuss. So these two will be fundamentals. Again, for a stress strain diagram, firstly, we'll talk about steel. So the diagrams obviously will be different for different materials. Then there are some specific topics about the behavior that material shows. We'll talk about a ratio, it's called Poisson's ratio, and we'll discuss about that as well. And then the shear stress strain diagram. So here is also the point. Same as the material has the axial strength by applying axial stress and getting axial strain, the material also has shear strength, right? Because once you're applying these slidings, the material tends to distort. So is it gonna be easy to distort your material or not? How strong is that material against distortion? So that is gonna be defined by another correlation between now shear stress and shear strain. And that is developed by shear stress and shear strain diagram. And then we'll talk about that as well. So let's start from the basics and fundamentals, the material characteristics, and we'll start with steel. Okay. So again, as I mentioned, the goal here is to characterize the properties, right? To measure the properties, measure the exact value of strength of a specific property. In our example, a steel property, a steel material. So obviously we have different types of steels, right? Different manufacturers produce different types of steels. There are different chemicals associated or um, inside a steel frame or a steel object. And the change of those chemicals change the properties of a steel. Actually, let's a little bit jump these slides and I can show it here. These are different types of steels. I will talk about these later, but these diagrams show different strengths. We have, and as you see, the percentage of carbon inside the steel material changes the characteristics of that steel, right? 1% carbon, 0.6%, 0.6%, 0.2, 0.1. These are called soft steel, structural steel, machine steel, hard steel, spring steel. So the chemicals affect the amount of strength that the steel has. So fortunately, we don't dig into the chemistry of these steels because also I hate chemistry and I don't like chemistry at all. So, and it's good that we don't get to the chemistry part of the materials. That's another major material engineering, I guess, right? You learn about the different chemicals of these different steels. But for now, we don't need to get in the basically microscopic level or in the molecular level. We just see it as a macroscopic level, right? Wider view to your material. So this is good for us. We don't get to the chemistry of the materials. We just know that, okay, so this is specific steel. The manufacturer produces this steel hard steel, okay? And the manufacturers give that steel in a shape of beams, for instance, and or columns, and you're going to use that in your building, beams or columns in your building. So once you're using that, you want to know what's the exact properties of that, what's the exact strength of that. So in order for that, we need to do some laboratory experiments, some laboratory tests on our steel. So for doing the laboratory test, obviously you don't want to bring a 30-foot beam to the laboratory. You don't have room for that. So you get a small sample of that steel, and that sample is in the shape of a bar, and they usually look like this. So it's in the shape of bar. And this is a standardized sample. So again, another note, we engineer love to standardize things. So this is a standardized sample that you can get from a manufacturer, and you can bring it to a mechanics of strength laboratory and test its strength. So how we test it? We put the sample inside a machine. The machine is called tension and compression machine. And in this machine, there are hydraulic jacks here. And by these hydraulic jacks, you apply normal loads to your bar. You apply normal loads to your bar. You can apply either tensile loads or compressive load. And then the machine also measures the amount of deformation that sample gets during that load application. And therefore, we would be able to calculate the stress and deformation in terms of a strain. And keep in mind, this is the type of the loading is the normal or axial loading. So we are now focusing on the axial strength of steel. So with this device, we are able to measure and evaluate the correlation between the stress that we are applying to our element and the strain that that element shows or experiences during the test. So I have a video here. I think this is video, right? No, this is photo. The video is here. It's a YouTube video. So this is the actual device. You see that the sample is placed here, and the device is connected to a computer. So these measurements can be written. Okay. So one point here is that for the stress that we are applying, so again, this is technical terminology. We put the force, but that gets to a stress. The stress that we are applying to this bar, we start from zero and we increase it incrementally, right? And so slowly we increase that stress, and therefore your material slowly starts to increase its length and it starts to have strain in it. So at any stage of the test, we can calculate the stress and the strain of that material. Based on the discussions we learned in section 1, the stress of that material is the force that the device applies to your element divided by the initial cross-sectional area of your element. So that diameter of element is 0.5 inch. Therefore, initial cross-sectional area is pi 0.5 power of 2 divided by 4. Okay. So the A0 is constant, A naught is constant. P again, it starts from P0 and then it gradually increases. So P gradually increases. That means your sigma gradually increases. So a strain is equal to a deformation divided by the initial length. So initial length, we are actually evaluating our actual element is from here to here. We are studying, we are having laser focus on this segment. And we measure the distance from these 2 points. So therefore, the initial length of your element, this is our element actually. These are the connecting points. The initial length of element is 2 inch, so 2 inch. And we consider that initial length to be same throughout the test. The deformation increases. It starts from 0 deformation and it increases incrementally. So then we perform the test, and by performing the test, what we are gonna do is we are going to record the values of a stress that increases incrementally and also record the values of a strain that increases incrementally. And at any point, we develop a chart or diagram. The vertical axis of that diagram is our stress. The horizontal axis of that diagram is our strain. Stress, strain. So at the beginning of test, we are here, right? There is no stress, and obviously there is no strain there. And then by applying a small amount of stress, we get to, let's say, this point. We have a little bit of stress on your element and then a little bit of a strain on your element. Again, by applying more load, you get to these points. So these gets increased. So you get multiple points during the test. And then by connecting these points together, you will get a diagram. The diagram is called stress-strain diagram. So this is, for instance, a stress-strain diagram of this specific steel that we are calculating or evaluating its characteristics. So at the beginning of my lecture, I mentioned that the correlation between a stress and a strain shows the characteristics and the properties and strength of your material. And here is that correlation that I was talking about. You get a diagram. That diagram shows the correlation between a stress and a strain. And that correlation or that diagram shows the characteristics and characterize the values and properties of that steel. Okay. So I'm going to pause my lecture here. And we learned that this is going to be a diagram getting from the tensile test. Now we are in the tensile test, right? We didn't talk about compression yet. So this is a tensile test. We get a diagram, and I want to, in my next lecture, I want to mention why the diagram looks like this, what this diagram tells about the steel, what's the story of this diagram, and how we characterize and what are the properties of this steel that we can read from the diagram. So the diagram has lots of details, and it shows the different behavior of a steel during the loading. Once the loading is small, the behavior of a steel is different. Once the loading gets higher, the behavior also changes. The last point here is once the steel breaks, right? Fracture. So steel just gets disconnected here, failure of the steel. Once the steel fails, your diagram stops. We get here. So we start from the 0 strain to here. That's the failure of our element. From this path, we see a lot of different behaviors, and we want to study these behaviors. And I think they are very interesting, and we are going to discuss it in the next lecture.